Now we are going to start with the 14th group of P block, right. So as you know that 14 group elements are carbon, silicon, germanium, tin and lead, right. We know that these are actually the members of carbon family because carbon is the leading member. So we have elements like carbon, silicon, germanium, tin and lead. So these all members belong to a carbon family, you know that. Right. So we are going to discuss we will be starting with the chemical properties, but before that we will just focus on the, you can say that the basic chemical nature of these elements of the carbon family. So first we are going to talk about the oxidation state. As you know that their general electronic configuration is Ns2 Np2, you know that, right. So if we look for the group oxidation state, then obviously the group oxidation state is going to be +4. But what do we see actually in this? Like if I consider carbon, as you know that carbon is smaller in size because it is the first member, so it is exceptionally smallest. So we see that because carbon is smaller, so it is very difficult to convert carbon into C4 positive, right? Because in converting C into C4 positive, we will require, like for removing first electron, we will be giving ionization energy 1, then ionization energy 2, then ionization energy 3, then ionization energy 4, right? So the sum of all these 4 ionization energy is quite high. And why it is high? You know that because carbon is smaller, so obviously the nuclear charge is more. So in order to remove 4 electrons is very difficult because sum of all these ionization energy becomes very high. So that means formation of C to C4 positive is not energetically favorable because that much energy is not available in a chemical reaction, right. So if I say that carbon can gain 4 electrons and it can form C4 negative, then also we see that this is also energetically not favorable. It is also energetically not favorable, but still you know that carbon forms certain kind of carbides with general formula C4 negative, like we have this thing calcium carbide. It exists in nature. We have silicon carbide, it exists in nature. So that means we have certain carbides which exist in nature where the carbon is existing in C4 negative oxidation state. Otherwise, it is also energetically unstable. So if we talk about oxidation state of these elements of the carbon family, we see that carbon exists in a state of +4. It exists in a state of +4, though it is energetically not favorable, but we have seen that it may exist in +4 or -4, right. If we talk about silicon, it also shows an oxidation state, that is in group oxidation state +4. But these members, right, they show oxidation state of +4 as well as +2. You know that as we move down, then the oxidation state which become more stable is 2 unit less than the group oxidation state. As the 4 electrons are there, so obviously the 2 unit less will be +2. So that means for the heavier elements, we know that the oxidation state which becomes stable is 2 unit less. So, and you are familiar with the reason we have done, that is the inert pair effect, right. So you know that inert pair effect is actually the reluctance in the participation of this Ns electrons as we move down, because due to filling of D and F, the nuclear charge, because they show poor shielding effect, so nuclear charge exceptionally get increased. So these electrons are tightly bound by the nucleus. So therefore they don't participate in a chemical reaction, only P electrons are available. That is why the group oxidation state is, the oxidation state that becomes stable is 2 unit less than the group oxidation state, right. So these you can say that this is all about the basic oxidation state if we talk about of the carbon family, right. Now moving on to the trends in the chemical reactivity, that what type of bonding they show actually. So we have seen that these group members, some of them show covalent bonding also and some of them show ionic bonding also, right. But what type of bonding they are going to show, that depends upon that which oxidation state they are making use of. As you know that their oxidation state is +4 and +2. So it depends on that whether they are making use of +4 when they are combining with some element, or they are making use of +2. So what we have seen that in +4 oxidation state, so you know that +4 they'll be having very small size, right, and they'll be having high charge. So obviously the bonding they will show will be covalent. They will form covalent type of bond when they are using their +4 oxidation state. But when they are using +2 oxidation state, so they are comparatively big in size. If we compare with +4, they are comparatively big in size, and their charge is, you can say, they are comparatively having the lower charge. So therefore, which type of bonding is favorable here? The ionic. So that means they form covalent also, they form ionic also, but that totally depends that which oxidation state they are making use of. If it is +4, then it is covalent. If it is +2, then it is ionic. Right, so this is all about the covalent and ionic bonding, that what kind of bond they are going to form. Coming on to the next thing, that what kind of character they are having, whether they are acting as an oxidizing agent or they are acting as a reducing agent. So again it depends upon the oxidation state. If they are making use of +4 oxidation state, then they act as oxidizing agent, right? And if they are making use of +2, they act as reducing agent. So that means they can act as oxidizing as well as reducing. That totally depends upon the oxidation state which they are making use of, right? So this is the +4 oxidizing agent, +2 reducing agent. Coming on to the next, this group actually has a property that they have tendency to form p-pi bonding. And you know that this kind of tendency is maximum seen with the first member, that is the carbon. As we know, carbon is small in size, we know that, and obviously it will be electronegative also. It will be most electronegative as it is smaller with increased nuclear charge. So due to this, you know that carbon has a tendency to form p-pi bonding, and it can form this kind of bonding, the double and the triple bond, with same kind of atom, that is with carbon also, and it may form with some other element also. So that means carbon has a tendency to form double and triple bond, that means p-pi bonding can be seen here. And it can be with its own kind of carbon atom, that is the same atom, that is the carbon, or it may it may happen with some other element also. And you know that due to this tendency only the catenation property of carbon is seen, and this is the reason that we get to see so many organic compounds in nature, and that is why we have a you can say a different branch of chemistry, that is organic chemistry, which is basically dealing with the carbon compounds. So this is the property which make the carbon special element, or you can say which led to the you can say another created another branch, that is the organic chemistry, where we study about all carbon compounds just because of this property. But as we move down, then a tendency to form p-pi bonding, however, decrease. Reason because they keep on becoming bigger in size. They are comparatively big in size than carbon, and obviously their electronegativity decrease. So that is why tendency to form p-pi bonding actually decrease down the group. That means when we move from up to down. Now talking about the tendency to form d-pi bonding, so we have seen that carbon cannot show this kind of bonding. The reason you are aware of, because carbon is lacking d orbital, you know that its atomic number is only 6. So that means it is not having any kind of d orbital, and if it is not having that d orbital, then how it can make d-pi bonding? So carbon cannot show this kind of bonding. But if we talk about the other members, we know that they have d orbital in them, so obviously they will be showing this kind of bonding, but their tendency to form p-pi bonding as comparison to carbon is very low, right? And but they can form d-pi, but carbon cannot form d-pi bonding, right? Because it is lacking the d orbital. So this is all about the basic you can say the outline of the chemical properties of the 14 group. So now just make yourself familiar with this, and now we are going to start with the chemical properties, where we will see the actual nature of these elements, which oxidation state they are making use of, and what kind of bonding they actually show, and what are the conditions that are necessary for the reaction to happen.